85. So that was right, and that's 0 at the top. So what we've got here is the electron. That's n equals 1 there. So here we've got the electron that is sat in this position here, let's say. Okay. And what Niels Bohr is saying is that if the electrons, or some electrons, are in this position here, some electrons are in this position, some electrons are in this position, and so on. So why would electrons be in these positions here? Now, if you're talking about hydrogen, it only has one electron, so it can't be in all four orbits at the same time. But when we've got hydrogen vapor, we've got millions and millions of atoms. Okay, so we've got hydrogen vapor, we've got millions and millions of atoms, and these electrons have been knocked into different orbits because the initial collision of incoming electrons has caused this. So let's say an electron is sat there in the n equals 4 position. What happens is that the electron could lose energy and end up moving down an energy level, moving from the 4th orbit to the 3rd orbit. The electron could also jump straight down from the 4th orbit to the 2nd orbit, but equally the electron could jump from the 4th orbit to the 1st orbit. When the electron changes its orbit or its energy level, this is called a transition. Okay, an electron transition. So when an electron moves in between energy levels, this is called an electron transition. So when an electron transitions between the n equals 4 to the n equals 1 transition, the energy that it has at the 4th level is equal to minus 0.85 electron volts, and it loses energy and it goes into the 3rd level, which has minus 1.51 electron volts of energy. So how much energy has it lost? It has lost approximately, so you do 1.51, so we're looking at minus 0. The amount of energy that is lost is minus 0.85 minus 1.51 electron volts, and what we get is 0.66 electron volts of energy that is lost when the electron goes from the 4th energy level to the 3rd energy level. Now, that is one possibility of the billions of atoms of the hydrogen vapor when the electron is in the 4th orbit and it jumps to, let's say, the 3rd orbit. It loses 0.66 electron volts of energy. Now I'm going to focus on just this for a few moments more. Now, as it jumps from the fourth level to the third level, so as it transitions from the n equals 4 to the n equals 1, it emits a photon. So when electrons transition from a high energy level to a lower energy level, a photon is emitted. So let's write that down, because that is a very important statement. I might have written that down in the presentation, but let's write that down. So when an electron moves, the word we can use is de-excites from a high energy level to a lower energy level, a photon is emitted with an energy equivalent to the energy difference between the levels. So the energy difference between the levels was 0.66 electron volts. That's how much energy that photon that's emitted has. Now, we know that the photon is a packet of energy equal to HF. Okay, so we know that the energy that the photon has is E equals HF. Okay, so we know what frequency the photon has when it moves from n equals 4 to n equals 3. And we also know that frequency is equal to the speed of light over the wavelength. So we know that the energy difference between the levels equals HF, or HC over lambda. We see that these are discrete energy levels, fixed energy levels. These transitions are between fixed energy levels. So the electron jumping from there to there, from there to there, has a fixed energy difference between the levels. That means that this photon will always have the same energy when it jumps from n equals 4 to n equals 3. That means this photon will have the same frequency every time the electron jumps from n equals 4 to n equals 3. That means the electron will have the same wavelength when it jumps from n equals 4 to n equals 3. Now this photon, this wavelength, shows up as a line on the emission or line spectra. So let's look at this now in reverse. This line has a specific wavelength based on the physics we have done previously on diffraction gratings. So this line, this red light that appears on the screen has a specific wavelength. Using E equals hf or E equals hc over lambda, we know that this red line has a specific energy. That specific energy corresponds to a transition or a de-excitation. So when an electron goes from high energy level to a low energy level, it de-excites or transitions from 4 to 3 in this scenario. And gives off a fixed frequency, fixed wavelength. So let's say that once more. We have got fixed wavelength on the line spectra corresponding to a fixed energy, considering E equals hc over lambda. That fixed energy corresponds to a de-excitation or transition from a high energy level to a low energy level, which are fixed inside an atom. That is the explanation you must provide to make the link between line spectra and the energy level diagram. Now, let's extend that. When the electron, let's stick with n equals 4 for a second. When the electron de-excites or transitions from 4, jumps straight to the second orbit, or n equals 2, that's a bigger jump. That means that the energy difference is large. If the energy difference is large, that means that the frequency of the photon that is emitted is higher. That means that the wavelength is smaller. Okay, so now we're moving from the red region to the green region of the spectra. If the electron jumps from, let's say, the n equals 4 level to the n equals 1 level, that's a bigger jump, bigger energy difference. That means that this photon is going to have a high frequency and even lower wavelength emitted. Now, that was just electrons moving from the n equals 4 level to the n equals 3 to n equals 2 to n equals 1. So from the 4th orbit to the 3rd, 4th orbit to the 2nd, 4th orbit to the 1st. As you can see, there are other possibilities. You can have an electron from the 3rd orbit jumping to the 2nd orbit, or the 3rd orbit to the 1st. and the second